So that's why the BZT also has a very similar kind of characteristics. So I should say that this experiment is will be easy for all of you because you already are familiar with different kinds of mostly this. The voice is clear, right?
No, sir. Sir, there are some noises there.
Yes, sir, it is not.
It is too sharp.
Not
Is it?
clear.
No, sir. No, sir. Not clear and noisy, and these are too sharp.
Oh, is it there? Okay. So should I explain again? Okay, fine.
Yes, sir.
Yeah. So again, for this experiment, I already have shared the manual as well as this one. Mm, manual as well as the videos regarding this one. So you know that you have learned about the bipolar junction transistor in the theory class, right? So I'm assuming that you already know at least the basics of the BJT, right? Please answer me. Hello.
Yes,
Hello.
sir.
My voice is clear right now.
Yes, sir.
Okay, so in this experiment, we'll have basically different kinds of, we'll do different things. First is the base emitter kind of IV characteristics of a BJT, right? So then we'll go for these collector base IV characteristics of BJT. Then also we'll try to find out, measure the current gains, which is alpha and beta, and then we'll try to measure the early voltage of the transistor, and then measure the different junction resistance of the transistor, like that. So it's quite similar to the diode experiments, because you know that BJT is also just the it's just similar to the diodes. It is also a PN junction, so it is also a combination of two PN junction, like we can have NPN or PNP. So that's why the behavior is quite similar to the some part is, of course, it's not diet is much simpler, and the uses of BJT is much more extensive than the diode. So because the BJT can be used as a digital switches, different designing different logic gates, different amplifiers. So BJT is, I should say, is the basics of the heart of electronics device. So the evolution of the electronic system, initially we had these vacuum tubes, right, which were so big and bulky. So with the introduction of the BJT, the revolution has started. And with BJT, after BJT, there's MOSFET. So, but the BJT, learning the basics of BJT is so important, because that's the heart. If you want to design any amplifier, right? If you will be using like amplifier, suppose in your projects in future, although you are from different department or from electronics, but some way or other in your projects you may come up with some signal processing or some signal amplifications. If you have to send some signals, because signals is like study of signals is there in all the field, and since now all the fields are quite integrated, we always use the electronic system, so you will come definitely across BJT or MOSFET, which are like the concepts are quite similar. So that's why and BJT is a 3-terminal device. Just give me a minute. I'll just get my pen. So BJT is a 3-terminal device, and we are supposed to, find out the characteristics between two terminals, as we have also must have, learned in the theory class that in a BJT we have the base emitter and collector. So by varying what parameter, what happens that you need to learn. So right. So we have this. My voice is clear, right? Hello, everyone. Hello.
Yes, sir.
Yes, sir.
This is an NPN kind of, you must have learned about the NPN, this BJT. So I have my, this is my collector, this is my base emitter. Of course, I'll not go too much into the theory. Here we'll try to come with the practical applications because this is an experiment lab class. So now we are supposed to discuss how do we apply it. So first we'll try to do the IV characteristics of the base emitter. So base emitter, like how, because this is like a PN junction, just like a diode. So by increasing the voltage across this base and emitter, there will also be an exponential rise in current, just like we had for the PN junction diode, because it's just a PN junction, P and N, just like a diode. The next is by keeping this voltage constant, how it varies. Like if I change this voltage, the VCE, how the current through this MOSFET, it varies. That is also that this is the second part of the experiment. And of course, we have to know what is the current gains. Like what is the gain of the current? Like if I have this current here, which is termed as base current IB, and my current IC. So what is this gain? So beta is defined as, if we have, I think it's discussed in the theory class already. So beta is defined as IC by IB, right? Then of course we need to find the alpha, which is beta by 1 plus beta. So those things we need to find it out. And the early voltage, we'll see about this. What is this early voltage eventually, right? So yeah. So in the LDSpice, if you open, you will see that there is this transistor BC547, which is an NPN transistor, right? So I request, like if you see in the, we have a recording of yesterday's discussion where I have demonstrated how to get this BC547 in LTSpice. So I request everyone to download it and then see the video like that. So this is for the NPN device. Or I'll give a very short demonstration. So I'll again demonstrate it, don't worry. So what here you need to do is, right, first you need to vary this voltage VB. So it's just a DC sweep. So this experiment is very easy. You just need to do multiple sweeps and that's it. So you need to fix this VC to 6 volt, right? You need to fix this VC to 6 volt, and you just need to vary this voltage VBE and plot the voltage across this base and emitter, which is basically the, if you plot this Vx, because Vy is already ground. So if you plot the Vx, then you'll get the VBE. Then just plot it, then you will get the similar kind of characteristics of a diode, because this is also NPN junction. So that's why you need to plot all those things. So you need to plot the VBE and IE like that. So yeah. So if you go to LDSpice, yeah. So if I just draw, I have drawn a simple schematic of this one. So you can, if you go to the draft, so this I already had drawn. So if you go to the components and if you just type NPN, definitely you'll get this NPN, this BJT, which is NPN. And just like in case of diode that you used to right click and pick a new transistor. So if you go and pick a new transistor, you will get BC547B. So which is from NXP manufacturer. So you just need to select that, and then you will have this kind of like that. So this is that I have shown. So this is how you need to use the BC547B for this experiment, right? So this is how you will be using this one, and you will be sweeping this voltage, and you will be plotting the emitter current IE and versus this BE. Any questions on this? Any questions? Everyone is listening? Hello?
Yes, sir.
Hello? Yeah. So, and for this case, you need to put BC equal to 6 volt and BC equal to 20 volt. So these are the two cases for which you need to plot this. Like, so you basically will get an exponential curve. So it's just like that you do like DC sweep of this VV, then you'll get this one. Then of course you need to do all these points. You can read this manual. It's and most important, just like in the diode, you have plotted the on resistance. So you need to plot the on resistance of that curve at a current IE equal to 2 milliampere, right? So at IE equal to 2 milliampere, you just need to plot the on resistance. So what you'll see here, you'll get an exponential curve, something like this. So at when I equal to 20 milliampere, you can just try to find a slope. So for slope, then you can just go up a little bit, go down. So you have this this delta x, this delta y. So plot the delta y by delta x. So that is basically will give by r 1 by r on, because this is current IE and this is VB, right? So so that's how you will find out the RVBE, or which also called as R on in case of the diode on resistance. Basically, clear? Is this clear? So
So
I'm
here,
not.
why we are taking we
Yeah.
are taking IA is equal to 2 milliampere?
Oh, it's just a point, like you just want to see that what is the on resistance. You can just like, because
Means any point we can solve.
you can use any point, but for this experiment, just for uniformity, we are taking I equal to 2 milliampere. It should not be too high or too less, right? So because you see the resistance, this RBB is dependent on IE, right? We know that the slope is dependent on this IE, right? So if I plot IE at 1 milliampere, then definitely my this RBB will be different. So suppose I have designed some amplifier and I need to set some value, right? So then and at that value I need to find out the RBB. So let's assume that I have set my design. My operating point is set at IE equal to 2 milliampere. That's why I have been asked like that. If my operating point is 1 milliampere, then I am supposed to find out the RBB at 1 milliampere. It's not so specific. Just for the experiment sake, we are making it a specific. Okay. If you want, you can change it. I don't have any problem. You can, if you want to plot at 3 milliampere, that's also fine. Getting? Hello.
This value we can choose ourselves. I is equal to.
Yeah, you can choose, no problem. Just it should not be too large. It should be at least in a range of 1 milliampere to 5 milliampere, not more than that. Okay, because that is generally the operating range of a BJT. Okay. Hello.
Yes, sir.
Okay. So next is we have characteristics. We have found out the characteristics of like how this voltage VBE is changing with how this this current this current through this junction V and E is changing through this potential voltage. So the next is how my current, if I'm fixing this this and this terminal fixed, how my current through this through this VJT is changing. How my current VJT is changing if I am changing the supply voltage, right? So in this case, what we'll do is we'll take two cases of this VBE. So by keeping this constant at 3 volt and 5 volt, what we'll try to do is we'll vary this VC, and we'll try to plot the current through the BJT, right? I suggest that you make this resistance to 0.1 ohm, so that this VCC will be equal to VCE, right? So VCE. So for that, what you can do in the LTSpice, you can just do this kind of connection. So I have already made this kind of connection, 47K ohm resistance, whatever is shown here, and 0.1 ohm impedance, and then VBB has been set to in this case 5 volt, or let's make it as 3 volt. So let's set it to 3 volt. Okay. And then I had made a simple DC sweep equation. So where my this V2 is varying from 0 to 10 volt with a step size of 0.1 volt. So this is a very simple DC sweep which we have done multiple times in the previous experiment. So I have not gone in much in detail. So, and I also have shown how do we set this transistor. So if I do the simple DC sweep, if I sweep this voltage from 0 to 10 volt with a step size of 0.1, and if I do this simulation, now what I need to do is I need to plot the current through this BJT. So I need to go here and then plot the current, right? So if I plot the current through this Q1, then you will see that IC Q1. So this is my IC Q1, which is showing the current, which is showing the change in the collector current with change in the this VCE. So you can see here there is a slope. So you need to calculate what is this value of the slope, which is explained in the next part of the experiment. Clear? Is it clear? It's very simple. You just need to vary this VC. You need to keep this constant VB to 3 and 5 volt, which is very clearly explained in the manual. You just need to follow the manual like that. Any questions on this? Any questions or clarification? Is it clear? Hello?
Yes.
Yes, sir.
Okay, great. So like that. So and what are you're supposed to do is very clear. Explain. Now what happens if you see this one? If you see there is a slope, right? So that's why I mentioned you need to calculate the slope, because ultimately you need to calculate the early voltage. So what is this early voltage? So the definition of the early voltage is, so you must have seen that here. So where is mine? So you must have seen here, right? There's a slope, right? Which you have to calculate. So this slope M is given by delta Y1, delta X1, right? This is the slope. And we need to find out the point on the x-axis where these lines are intersecting, basically. So basically you are supposed to find out the delta X2, right? So we know that M equal to delta Y1, because the slope of this whole line is constant, right? That's why if you can find out the point where this line is intersecting the y-axis, definitely you can find out this y2. So what you're supposed to do is M equal to delta y1 by delta x1 equal to delta y2 by delta x2. So if you want to find out the VA, which is basically the delta x2, right? VA equal to delta x2 is equal to M into delta y2, right? So by using the simple slope equation, you can find out the early voltage VA. Is this clear? Is this point clear? Hello? Or should I explain it again? Hello? Hello? Should I explain it again once more?
No.
Okay, and the value of the RCE here is nothing but RCE is delta VCE by delta, delta IC, which is nothing but it's same as delta X1 by delta Y1, right? So this also will give you the this collector emitter resistance. Basically, the slope. This inverse of the slope is the resistance of the collector emitter resistance RCE, and of course you need to find out this early voltage VA.
So VA will be delta Y2 by M or delta Y2 into M?
delta y2 into m, VA. So VA is equal to x2, right? Is delta x2. Following?
Yes.
Okay. So you see, if you see this triangle, right angle triangle, and this right angle triangle, right? They have the same slope, right? M, slope is m, slope is m. So that's why the slope, the definition based on the definition of the slope, that's a simple definition, right? Based on +2 mathematics. So that's why, right? Okay. Yeah. So that's why it's very simple. You just need to calculate these stuff. It's not difficult at all. And finally, you're supposed to measure the current gain. So let me delete and explain once again. So what is this current gain? So basically, the current gain is the ratio of your this current. So this current IB and IC. So that is my beta, right? So if I call this as IC and this is as IB, so beta equal to IC by IB. So that's why what you're supposed to do is you slowly vary this voltage from 3 to 5 volt, right? And then for different values of the BB, you can just plot what is this current. You can just plot the current by doing DC sweep also like that. You can directly get actually, or DC operating point. You need to fix this voltage to 15 volt, right? 15 volt. That's why it is mentioned here. And then you find out what is this current IC, and then the beta is nothing but IC by IB, right? And of course, you are supposed to measure the alpha also. So alpha is nothing but once you measure the beta, alpha is beta by 1 plus beta. So that's the equation of the alpha. So right, this is also very simple. So you just need to vary this one from 3 to 5 volt, 3 to 5 volt, right? Keep it varying. Measure this current IB and the corresponding IC and find the ratio. So which is the beta, basically the current gain. So for example, here you can see that this is an example. So 3 volt, you have a current IB of like that, and then you have this current IC. So take multiple readings, around at least 5-6 readings between 3 to 5 volt. Do simple DC operating point analysis, right? And you can even plot the, of course. You can plot IC and IV, and this because this slope is the ratio. So either you can take this ratio. This also will definitely give the slope because this line basically goes. It is assumed that it goes through this origin. So any point here, like the slope of the graph or the ratio of the IC by IB will give you the beta. The slope is also equal to beta, or even if you just take simple ratio, that also will give you the beta value. Okay, so that's it. So this experiment is, I should say, it's pretty simple compared to whatever all of you have done. So you just need to make two observation, of course, not table is not required here because you will get directly graph here. So if you are doing in the lab, this experiment is tough because you have to take so many readings. But if you are doing in simulations, it's very easy. You just need to change this voltage to 6 volt and 20 volt, and then plot IE versus BBE, so which I have explained already. Then IC versus BCE, which I also have shown with the demonstration. And then you need to plot the IC versus IB, which will give you beta by changing BB, right? So, and from the plots, you have to get this. I have mentioned how do you get this early voltage. The base emitter resistance is just like how do you calculate the on resistance of the diode. The early voltage is by understanding the slope and which is the x2 equal to m into delta y2, which I have mentioned. Then the collector emitter resistance is nothing but delta VC by delta IC, which is also the inverse of the slope for the case of the early voltage. Then the current gain beta is nothing but the IC by IB. That you need to see it for different values of IB when you are changing BBV from 3 volt to 5 volt. And of course, the alpha is nothing but beta by 1 plus beta. And then you can just briefly explain your calculations. That's it. So this experiment is quite simple. So I don't know next week whether we'll have class or not, because I think the mid-sem schedule is out now. So did you get the mid-sem schedule? Hello?
Yes, sir. It is from 7th. That means next Wednesday.
Yeah, next Wednesday we don't have any class. So you can submit your report peacefully till next Wednesday. So, and I think you can better you start doing the experiment now itself. You can just plot down the readings. So it's very simple. Do you feel it's difficult or simple? Hello?
Sir, when we need to submit it?
By next Wednesday. Submit by next Wednesday. So in case if you want more, if you want, you can even download yesterday's recordings. So I think yesterday I had discussed a little more elaborately. That's why I wanted to play the video. But yeah, I spoke the same stuffs, but maybe a little more in details. So if you want, you can download that video, or I can also share the link, whatever I wanted to play today. So that's little more elaborate, but these are same thing, same stuff only I discussed. If you have missed some points, then you can download and you can see it again if you have missed. Again. Okay. Any questions? Any questions for me? Okay, then I'm available now, right? I'm available now till 5. You can start doing the experiment. If you have any questions in between, you can ask me, right? And I already have shared the manual in the website, right? So please start doing it. If you can do it, if you can do it, it will be better now, so that you can ask the doubt now itself. I'll be available till at least till 5 o'clock. So, okay. Okay.
Hello, sir.
Hello.
Hello, sir. Can we submit this lab record after midsum, like from Tuesday? We are having our midsum exams.
Okay, fine. Fine. I'm okay. I'll tell the other also. But no, it's better that at least you do the experiment, right?
Yeah.
Sir, excuse me. Here,
We
sir.
have to prepare for ourselves for
Hello.
midsem. We have
Sir, I am telling that when we are giving the exam, so
Hello.
sir, excuse me, after the exam, our exam will be completed on 15th. So when we are giving the it is on the Thursday, so we are going to submit our we are going to the next lab after the 15th, that is that after the 15th, that Wednesday, that is I think that is on 20th 21st. So
Okay.
if we submit that on the Thursday, we are completing our exam. So if we submitting as usual on this on that Sunday, that means the after exam that Sunday. So as usual, it is keeping the intact. So no problem, I think, with it, because we are submitting on the Thursday and this Tuesday or after the lab, it will be same cell.
Okay, fine, fine, fine. I agree. I got your logic. So it's okay, like fine. So I'm giving some relaxation because I know all of you have exams and pressures in there.
Thank you, sir.
So you can submit. What is your name? Please tell your name whenever someone is speaking. Somyajit, right?
Yes, sir.
Okay, so yeah, I'll just circulate a mail to everyone, so everyone gets this information. Even for the Tuesday's batch also I'll tell. So okay, any more questions? Any technical questions on this experiment? Any doubt? Please ask your question before Friday. If you have to mail, if you mail on if you mail on Sunday, Saturday, it is difficult for me to reply. Anyways, my inbox gets filled with so many other mails, so it's better you mail me before Friday, because I also need some time to respond, right? So it's not that I've seen like some people asking me question like 3-4 hours before the deadline. I won't be available at the time, right? 9 o'clock, 10 o'clock. So it's better you do your experiments before, and then you can do now also. I think it's better you do now so that you don't have to you'll not be pressurized later. Okay, I'm available. Mention if you have any questions till 5 o'clock. Yeah.
Sir,
Yes. What?
sir, in the early voltage part, that you told that early voltage delta x. So m equals to delta y by delta x. So delta x will be delta y by m, I think.
Just
So it will be delta y by m.
uh-huh. So, let me go back. Okay, I've had some mistake. What's your name? Can you tell me? Hello. What are your names?
Shubhajit Banerjee.
So was it right? Yes, you're correct. Yeah, I made this mistake. Yeah. So yeah, delta x is yeah, x2 is delta y by m. Yeah, I just yeah, you're very correct. Thank you for correcting me. Hello. Yeah, yeah.
Yes, okay, sir.
Because
Thank you.
because this yeah, I think I have not mentioned this. I had freshly written this one, so yeah, I think that whatever I have uploaded, this mistake is not there. Anyways, thank you for correcting. What are your names? Can you tell me?
Shubhajit.
Subhojit and other one.
So
I
Ayushi.
yeah. I think I should take note of those students who are proactive in class and they're correcting me. Yeah. So I'll definitely note down all your names. I think if it would have been in a normal class, it would have been nice interacting with all of you. But so please go to the manual and ask me questions in next, as I'm available in next 45 minutes.